In this video, I'm going to talk about artificial intelligence, machine learning, and some of the issues that these raise for journalism, as well as some of the opportunities and some of the jargon involved. For example, deep learning, NLP, supervised learning, unsupervised learning. You'll come across a lot of this sort of jargon in technology generally and in data journalism in particular. So I'm going to talk about what those mean and how they can be used for journalism, including the field of algorithmic accountability. So let's begin with some basic definitions, and perhaps the first one to tackle is how to separate those two terms, artificial intelligence and machine learning. They're quite often used interchangeably because a lot of modern artificial intelligence is machine learning, but they are actually quite distinct concepts, and I would probably advise against using AI generally because AI is a very broad term. It covers a lot of different technologies and techniques. It's been around for a good 70 years or so, and it includes very basic simulation of intelligence like chatbots, for example. So any script that mimics some sort of intelligent actions could be described as AI. Really, a lot of the more recent developments have been in this field of machine learning, which is a particular subset of AI that relates to the process of writing scripts or algorithms that allow a computer to learn things that we as humans might not actually know, or at least be able to instruct a computer directly to do. For example, image recognition. It's not an easy thing to teach a computer how to recognize a dog, but machine learning is a process of allowing the computer through some script to understand the characteristics and learn the characteristics that it might understand as being a dog. But before we get into machine learning, let's start by covering some of the areas where AI is used more broadly within the news industry and indeed within society more generally. And it's used in all sorts of contexts. It's used to categorize things, it's used to solve problems, identify those problems and try and find the best way to solve them. It's used for planning and finding the optimal way to plan a sequence of steps. It's used a lot in translation and language, and it's used, as I've mentioned, in things like image recognition and image identification, facial recognition, for example. This is how cars are able to see, for example. It's the process of recognizing some sort of object because of the combination of pixels on the screen. Within the news industry specifically, it's used at all stages of the production process. In terms of ideas generation, for example, AI can be used to flag anomalies in data sets or tell us how the audience is behaving and things that it might be interested in. It can identify trends that we might want to report on. When we come to research stories, it can play a role in verifying or validating the information that we're looking at or scanning through data sets. There's an increasing amount of AI tools being used in journalism production. For example, at a very basic level, automatic translation or transcription services are based on AI technologies, but also there are tools that will take a script and convert that into a video by selecting images from some sort of archive. There's automatic visualization that does the same with data. And then in terms of publication, we might use AI scripts to determine the time of publication or even the platform. It might be used, it's quite often used, to recommend stories to individuals based on learning from their previous consumption. And it's also used in terms of comments as well and interaction with audiences. So for example, chatbots, which we've mentioned, or it might flag up comments that are likely to need moderation, or indeed it might automatically hold those comments back. And finally, we've got archiving as well. AI has played quite a big role in adding new value to archives by tagging them, identifying relationships between them, and making it easier for journalists and researchers to explore archive material. Now, in terms of the kind of balance of how AI is used in news, it's very much towards the commercial side. Really it's not used as widely in editorial purposes or for editorial purposes as much as it is used for things like pricing adverts or recommending content to users. At a very low level, a very basic level, it is used for things like alerts for journalists. So if you're looking at tools like Data Miner, which will identify tweets or Facebook updates that are likely to be newsworthy, it does play quite a wide role there. But anything more complex than that, it tends to be a more minority application than some of the more commercial uses. But we've mentioned image recognition already, and that's probably one of the best known examples of the way that AI is used. And in some cases, it's been found to be more effective than humans. One thing that's very useful to know as a journalist is that Google image search has some AI technology built in. So you can actually search for number plates and it will find number plates or indeed signs that have text on them. You can search for the text and it will find images that contain the text that you're looking for. And it does this, in fact, the technology that it uses to do this is available to the general public as well. This is the Google Vision API, and you might remember in a previous video I touched on this for a BBC story which looked at racy images and how likely images were to be classified as racy by Google's Vision API, or its AI technology. And you can see that this AI is used to classify images in a number of ways. So how likely the image is to be an adult image, or whether it's likely to be a medical image or a violent image. But also we've got the text extraction that I mentioned. Here's an example of an image being read, if you like, being seen by AI technologies on Google. And you can see how this is working effectively at the bottom, but also how it can make mistakes, like seeing the number 17 in some knuckles. And you can also see up here we've got faces, we've got face recognition, object recognition, and so on. So in terms of object recognition, you might have Google looking at an image and seeing a door, a picture frame, a bicycle, and components of a bicycle as well, like the wheel and the tyre. You'll notice as well that it's not necessarily always correct. So would you describe this as a picture frame? Probably not. It's more of a sign really than a picture frame, but we can also understand why it's recognized it as a picture frame. And this has been put into practice by a number of news organisations. This is probably a good example to show you is at the royal wedding, where Sky News used image recognition. They trained an algorithm to recognise celebrities who were likely to be arriving at the royal wedding, and then as they arrived, the algorithm would pick them out. So we can watch this video as it played on Sky's website, and you can see it identifying the individuals that are arriving. So this is image recognition in action. What's happened here is that the staff or a team at Sky, or at least at a company that they partnered with, have compiled a list of celebrities, and they fed images of those celebrities into a classifier. So they've essentially trained an algorithm on a set of images of people that they thought were likely to, or indeed knew, people that they knew would be at this wedding. Now, they would have had to have fed in multiple images because we don't know what angle that the camera is going to catch these people at. And the computer is picking up different features of these people and trying to understand how to recognize them. Now, I was listening to one of the people involved in this talk about the process that they went through in creating this tool and some of the problems that they had. One of the problems they had, for example, was that one of the relatives of the couple getting married, there was a couple of twins, identical twins. Well, identical twins look the same. They might dress differently, but even humans sometimes struggle to tell them apart. So in that case, they had some details about those individuals and how to tell them apart, and humans would intervene when the computer identified one of those two twins. There was also a famous rugby player who had broken his nose many years ago, and most of the pictures that they had, in fact, I think all of the pictures that they had of that particular sportsman, had his nose, this kind of broken nose, but actually he'd had that nose fixed shortly before the wedding, so they knew that he would look different and would not be necessarily picked up by the tool. So again, not perfect, but quite an interesting application of it here, and also a classic example of a big event, a big news event, justifying some technological experimentation, which happens very often. You often see technological innovation at the Olympics, at the World Cup, at US elections, and so on. One of the other applications of this technology is that you can select a particular personality. So let's pick Joss Stone, and then after this event has happened, you can read a little profile and then click on Watch Arrival, and it will skip to 20 minutes in when Joss Stone arrives. So it's not only performing live and helping the viewers and indeed the journalists to recognise who is arriving at this event, but it's performing an archiving function. It's adding metadata to this video material, which makes it easier and more efficient for journalists in the future to fetch clips of these people if they were doing some story about Joss Stone or about the royal wedding, or indeed both together. So image recognition is just one application of AI, and we'll talk a little bit later about how that works in more detail. But first of all, sticking with AI more broadly, there's a Tau Center report from 2017, which is worth reading if you want to look into this in more detail, that looks at the applications of AI in newsrooms editorially. And they identified three broad applications. The first is the idea of finding needles in haystacks. So we're talking here about big document dumps or massive data sets where you're looking for something interesting in that large set of information. That's something that AI can be particularly effective at. Likewise, it can be used to identify trends in large data sets, or indeed departures from those trends, outliers. The third application is really more about looking out at the world as a whole and the use of AI in the world, and using AI as journalists to hold that to account, to scrutinise it. This is a field that's come to be known as algorithmic accountability, and again you can read more about that in either of these links. The first is a primer from Data and Society, but the second, Nicholas Diakopoulos, who's a leader in this field and in automation generally, he's written another Tau Center report on algorithmic accountability reporting and some of the processes that are used to investigate the use of algorithms and AI in society as a whole. And this is because AI has become essentially, or algorithms have become a source of power themselves, a form of power to be held to account by journalists, of course. A report from 2017 on AI called AI Now, which comes out every year, highlighted this. It highlights the way that AI was changing the balance of workplace power and coming to replace, or had the potential to replace, more democratic forms of bargaining between workers and employers. Now, you can see examples of this all around. The gig economy is one particularly good example, the way that prices are set by algorithms, so that taxi drivers for Uber or owners of flats using Airbnb are subject to the whims of the algorithm in terms of changing the prices that they get paid for their work, rather than being able to negotiate with some sort of employer. And obviously you can see it in other systems as well. Crime in particular has been one of the areas most heavily scrutinised when it comes to the use of algorithms and AI. And ProPublica have been at the forefront of this. Their machine bias series, which again is well worth looking at to get an insight in probably into some of the best algorithmic accountability reporting out there. This looked at the use of algorithms to determine or influence sentencing of criminals. And what they found was it's biased in terms of race, based on the race of the person that was being accused or being sentenced for crime. Now, one of the things, again, a recurring theme with this, and the thing that they found with machine bias was that one of the problems with algorithms is the data that's used to train it, in other words, the data that a computer learns from, is itself represents human behavior. So I'll come to machine learning in a minute, but this is the idea that we're encoding human behavior in an algorithm rather than necessarily addressing some of the issues of that human behavior. But you could say that the rise of algorithms has actually drawn our attention to our own biases by encoding it. So let's come on to machine learning, which, as I said, is one particular branch of AI and probably the one that you're going to come across most. And this is the idea that essentially a lot of the time we're helping machines learn by letting them find strong relationships, strong correlations. So really it's, I love this cartoon because it puts it perfectly. It's really a very fancy form of statistics. We're using a form of regression analysis or correlation, but we're doing it in a very complex way. And we're letting machines learn from that instead of ourselves identifying correlations and talking about it in the ways that we would do in the past. So again, to kind of re-emphasize, machine learning is a subset of artificial intelligence. And what I'm about to do is drill down into some subsets of machine learning. There are 3 branches of that: supervised, unsupervised, and reinforcement learning. I'll go through each in turn. And then there's also deep learning across all of those, which I'll touch on as well. Before I go into those 3 branches, it's worth touching on these 2 key concepts of training data and test data. A lot of machine learning relies on, first of all, having a data set to train the computer on. In the example of the royal wedding algorithm, the creators of that tool had a training data set which consisted of photographs of lots of celebrities or royals and the names of those royals, of course, in order for them to be able to associate an image with a name. Likewise, we might want to train an algorithm to predict whether someone was likely to pass or fail their driving test. In order to do that, the training data might be something like data on thousands or millions of people who'd taken their driving tests. We'd want to know whether they passed or failed, but we'd probably have other data in there like their age, their gender, where they were from, what job they had, what date they took the test on, even what weather the test had, what location they took the test, and so on. Now that training data is normally split up so that part of that data is held to one side to test whether the computer has learned, or indeed how effectively it has learned. So for example, if we had images of all the celebrities that we were expecting at the royal wedding, we might train it on 80% of those images and then save 20% of the images to test it, because it won't have seen those images before. And with both of these data sets, we need to know we need to have them probably classified, or at least if we're using supervised learning. And supervised learning is the process of essentially teaching a computer or an algorithm to identify something or to classify something or to be able to calculate a probability. Here's one very good example from BuzzFeed and Peter Aldous around spy planes. What they did was they created a training data set of planes that they knew to be spy planes. So we're looking to train a computer to identify spy planes, and we do that by giving it some information about spy planes and how they behave, for example, their flight path, what time they take off, and so on and so forth. Once the computer has learned to recognize the features that characterize spy planes, then we unleash it on some other data, which would probably be of lots and lots of plane flight paths, for example, and we don't know which ones are spy planes. The key thing here is that in the training data set, we've classified which ones are spy planes, or at least we've already manually identified which ones are spy planes. And we don't know what characteristics the computer is going to find. What we're going to do is we give that data to the computer, and then it learns. It might be any sorts of combination or weighting of different factors that distinguishes a spy plane from a non-spy plane. And we test it on the test data set until we're happy with a certain level of accuracy. It might be 90% accurate, for example, and then we unleash it on some data that we haven't classified, because we want that algorithm to classify it for us. So we might train it on 1,000 rows of data and then unleash it on 1,000,000 rows of data. And in fact, you can see in the text here, it's 500 rows of data, 500 planes there, and 97 spy planes, so about 600 in total. Here's another example just to kind of re-emphasize the point. This was an investigation into the scale of allegations of sexual misconduct. Now, there was no, if you like, reliable data on this, so what they did was manually classify thousands of disciplinary documents, and they classified them in terms of whether they were or were not involving sexual misconduct, and then used that as a data set, a training data set, to train the algorithm to identify what features might mark a document out as being likely to be about sexual misconduct. So it might be the mentions of certain words, certain phrases, even certain names. We don't know, or at least we don't know to begin with until we let the computer try to learn from them. Again, once it's achieved a certain level of accuracy, it's unleashed on the full data set. So what we're really ultimately interested in doing here is classifying hundreds of thousands or millions of documents so that we can establish the scale of a problem. What's important to emphasize here is that we're not going to be able to identify precisely the scale of the problem. If it's 90% accurate, then that means that there's margin for error. So it might say that it thinks that there are 10,000 documents, 10,000 instances of sexual misconduct, but we know that the real figure might be 11,000 or 9,000, and so we need to factor that into the way that we tell our story, and also we need to make sure that that's a meaningful margin of error, that we can still tell our story. It's still going to be accurate even within that margin. Another example of supervised learning is, again, with images this time, is the idea of giving different ages to people. So in this case, we would train the algorithm on a set of images which had a name, an age associated with them. So again, it would try to calculate the age based on the image. It would achieve a certain level of accuracy, and then we would try it on some other images that it hasn't been trained on. In this particular research paper, you can see it's actually not a very accurate algorithm, but that's fundamentally the process. Supervised learning is more easily understood when you compare it with unsupervised learning. In unsupervised learning, we don't know the classification or the calculation that we're trying to get the computer to do. So whereas in supervised learning, we're essentially saying we've classified some documents, or we've attached an age to some celebrities or a name to some people. we're really in supervised learning, we're asking the computer to then repeat that process at scale, to learn how to do what we did and then do it at a scale that we cannot do as humans. In unsupervised learning, what we're asking it to do is find the patterns that we don't know exist in the first place. So we're not asking it to classify, we're not asking it to calculate, we're asking it just to find patterns, any patterns that might, hopefully, lead us to some sort of story or something that we can investigate further. So this is the needles in the haystack sort of situation. This example that's on the slide here is an application of unsupervised learning to Wes Anderson films. So in this case, an algorithm has been fed images from kind of still images, say every 10 seconds for a number of different films, and asked to essentially identify any patterns that it can find. And what it's found is a pattern of different colour palettes that's used in the films. So as an arts journalist, this might be the starting point for some sort of feature about the use of colour in Wes Anderson films. We might focus on a particular pocket of these and tell our story about that, or we might look at how these have changed over time. So it's about finding patterns that might provide the basis for further exploration. In this example, Instagram used unsupervised learning to look at emojis. And again, you can see the clusters that have been produced here have grouped together similar emojis. So what this means is that these are the emojis that are used in similar ways. So it's not the fact that the algorithm hasn't looked at these and thought, oh, these are all faces, I'm going to put them together. This is more about how these emojis have been used in messages or in captions on images. They seem to be used in similar ways. And certainly the face emojis are used more often, for example. But we also have a food cluster, we have a countries cluster, and so on. Now, the third type of machine learning is reinforcement learning. And this is, unlike the other two types, this is more about solving some sort of problem, or at least finding an optimal path from A to B. This is classically used in things like computers learning how to win games, so how to win a game of chess or something like that. What will happen is it will play lots and lots and lots of games, it will lose a lot of them, but along the way it will learn what types of approaches, so what series of steps tend to lead to success and which ones lead to failure, and so it will reinforce the processes that lead to success, and then eventually it will become better than the human. Now, this hasn't been used in journalism very much at all, and you can understand why. It's really not a process that does make sense for a lot of journalism situations. The only example I can think of is a New York Times interactive where you were invited to play rock, paper, scissors against a robot and it would beat you. And the idea is that it would beat you because you're not random. You would have a certain way of playing and it would eventually learn that way, and then it would learn how to beat you. So just to summarize those three types of machine learning before I move on to some other related jargon. What we've got here then is supervised learning, unsupervised learning, and reinforcement learning. Reinforcement learning, as I said, is about games, it's about route finding, it's about optimal processes, optimal routes from A to B. Supervised learning is often used when you want to classify something, so you might want to classify documents as being of a particular type, or it might be to do with regression, so this is a sort of a calculation, like a classic example is calculating the value of a house based on various metrics. So there's a regression, a mathematical relationship between all of those values and the eventual value of the house. And you might have, this might express itself as something like the likelihood that someone might pass their driving test, or the likelihood that someone might commit a crime, or whatever it is. Unsupervised learning is more about association and clustering, those kind of needles in haystacks type situations. So let's now move on to a couple more pieces of jargon, a little bit more deeply involved in machine learning, and those are NLP and natural language processing and deep learning. First of all then, NLP. This refers to a series of technologies that are used to deal with language. It's the sort of technology that's used in converting text to speech or translation or transcription. It's used in speech recognition. It's essentially what's used in predictive text and things like that. There's a subset of NLP called NLU, Natural Language Understanding, and that involves things like sentiment analysis, which is where an algorithm tries to understand whether a sentence is positive or negative. So you might have a sentence like this, which is interpreted by NLP in a number of ways to extract entities and even intention and relationships between entities. Now, NLP can be used for both supervised and unsupervised learning. In a supervised learning task, for example, it might be used to classify text, so whether it's spam or not. In that sense, you might feed an algorithm all sorts of examples of emails which are spam, as well as emails which are not spam, and it will learn the qualities that allow it to classify text as being spam-like. You can also use it to perform a sort of regression, like it's 90% likely that the next word is going to be the word love or like. Again, as with other machine learning techniques or AI techniques, one of the key problems with NLP is it's got to be trained on some sort of data set. And with NLP, it's trained on text, what's called a corpus of text. And it's often trained on text that's even if it's trained on text now, it would reflect stereotypical word associations, but often the text is from the 1990s or even older, which reflects stereotypical associations of the time. So we need to be conscious of that if we're using these techniques. But there's been some really interesting applications of NLP within journalism and within machine learning. This was a really interesting example of a project. I don't think they actually were a journalist, but it certainly was journalism. And this was the idea of looking at comments submitted to a regulator, which was proposing, or at least it was opening a consultation on net neutrality, the idea that everyone should have, that there should be no sort of two-tier system around access to the internet where you pay more for to access certain websites, for example. Now, they received about, I think, over 2 million submissions in their consultation, and this particular person analysed those submissions for very similar submissions. In other words, bots. They were interested in whether this process was being hijacked by automation, and what they found was that almost certainly was happening, and they did that by essentially using unsupervised learning and NLP to look for clusters of very similar submissions. So they didn't know what these would look like in advance, but they essentially said to the computer, please show me clusters of pieces of data, and the data here are documents, submissions, collections of words. Show me submissions that are similar, show me clusters, and what they found was these clusters that were probably being automatically generated. This is another example. This is from an analysis of some websites in Ukraine and political manipulation of these. So you can see this is looking at the headlines of websites that were essentially kind of Russian or at least troll farms, that sort of thing, or fake news farms, websites that were being used to stir up misinformation. And you can see the identification of themes here. So what this is doing is, obviously the word in the article itself isn't government or politician, it is the name of or some word related to these concepts, but NLP is able to understand that all of these different words can be summarized under this particular theme. So 50,000 manipulative news articles, and they're clustered according to headlines. And if we go through, it actually zooms in to the different themes that are identified in here. So that's something else that NLP could do. It could cluster, create clusters, identify clusters that allow you to tell a story about the makeup of a corpus of information, in this case, trolls or fake news or misinformation. Spotify uses NLP as part of a combination of algorithms in the way that it recommends music. And in this case, well, we don't know exactly how it uses it, but it could be a similar way where it clusters music together based on some sorts of shared features. So let's move on now to the other piece of jargon, which is deep learning. Deep learning is, again, a subset of machine learning, a particular way that you can do machine learning, and it's intended to replicate the way that the human brain works by sort of creating virtual neurons and weighting the connections between those neurons in order to create a machine learning outcome. So it uses what's called a neural network. Neural network sounds very similar to the way that neurons are used in the brain. It often has many inputs, and it starts quite badly. It doesn't perform well to begin with, but it improves very quickly. And the reason for that is that it uses a lot of power and it uses a lot of data. Now, until very recently, it was quite expensive to get access to both of those, the large amounts of data and large amounts of power, but those have become increasingly acceptable in recent years. The big problem with neural networks and deep learning is it's quite difficult to explain how you got from the raw information to the final results. Now, you can find out more about neural networks and deep learning in this video, and there's a subsequent video as well, which I've embedded in the slides. So I just want you to introduce you to the key concept and point you to some resources to find out more. But one of the key issues, as I said, is this idea of explainability. In this chart, you can see, ironically, it's not a very easy chart to understand or explain, but what we've got is a number of different techniques used in AI. So we've got deep learning here, neural nets, we've got Bayesian belief nets, we've got ensemble methods and so on. And each of these is mapped on this chart in terms of its explainability and its prediction accuracy. So we can see that deep learning is one of the more accurate methods. It's very powerful, but it's also the least easy to explain. It's got the lowest explainability. Decision trees, in contrast, are probably less accurate, but are more easy to explain. And decision trees are quite useful to move on to in terms of journalism because of that explainability. They help us to tell a story in a way that may be more important than being accurate but hard to explain. And obviously this will depend on the editorial situation. To illustrate this, here's a couple of examples. This is a piece of journalism by Haluka Meyer-Borst for the FT looking at the German elections. And you can see the accuracy, you can see the low accuracy of this model. This is a model which is looking at how easily you can predict how someone is going to vote in the election. So it's a, as they put in the description, a machine-based profile of German party voters. And so that's essentially the story. The story is about, well, based on whether someone lives in the west or east of Germany, based on what percent of people on the street are foreign, you can kind of predict how someone is going to vote. And it varies from party to party and from question to question. So to some extent, the story here isn't necessarily about predicting who's going to vote in the election. It's actually about how predictable different groups are. So this is a prediction for one particular party and its voters compared to other voters. So in this case, the decision tree, this is what a decision tree looks like. You make decisions and then it leads you down a certain route. The decision tree is a narrative form. within data journalism and machine learning. This another example comes in this investigation by the SRF data team, which is looking at celebrities or influencers on Instagram and how many fake followers they appear to have. In this case, the machine learning is used to identify the likelihood or the likely volume of the fake followers, and then that's used as a starting point to go and interview this influencer and kind of present that finding to them. And it's quite a good example of using machine learning to come up with a sort of a hypothesis, or at least an evidence base, but the actual story is in the reaction, because these people don't necessarily deny that they are buying fake followers. And in this video, you see them explaining the decision tree that allows them to perform this calculation.
Decision tree lernt nachher selber, wie er zwischen Fake und Nicht-Fake unterscheidet. Zum Beispiel ist ein Follower eher Fake, wenn er mehr als 600 Leute folgt, aber selber weniger als Decision und nicht 32 Kilogramm schwer. Jetzt aber zum Algorithmus. Die Grundlage ist ein sogenannter Decision Tree. Damit der Decision Tree zwischen Fake und Nicht-Fake unterscheiden kann, muss man ihn trainieren. Das heisst, wir zeigen dem Decision Tree 1000 Follower. Von diesen 1000 Follower wissen wir schon, ob sie Fake sind oder nicht. Der Decision Tree lernt nachher selber, wie er zwischen Fake und Nicht-Fake unterscheidet. Zum Beispiel ist ein Follower eher Fake, wenn er mehr als 600 Leute folgt, aber selber weniger als 10 Fotos gepostet hat. Der Algorithmus macht natürlich auch Fehler und stuft ab und zu einen Follower falsch ein. Darum haben wir ganz viele von diesen sogenannten Decision Trees aneinander gehängt und durch die lassen wir jetzt alle 7 Millionen Follower. Am Schluss nehmen wir den Durchschnitt von dem. Und das nennt sich der Random Forest. Und der Random Forest hat eine Genauigkeit von 94%. Das heisst, er kann 94% von unseren 7 Millionen Follower korrekt einstufen.
Kommt aus, rund 1/3 von allen Followern, die wir analysiert haben, ist Fake. Bei mir sind 2/3 Fake, das weiss ich, weil ich die ja auch selber gekauft. Aber ob die richtigen Schweizer Influencer das auch wissen, können wir jetzt herausfinden. Also schau, wir haben ein probes Exempel gemacht, natürlich. Ja. Und wir haben herausgefunden, es ist massiv viele falsch, auch in der Schweiz und auch bei dir.
Aber das habe ich einfach nicht gewusst. Weil ich habe nie gekauft. Nie. Hey, das ist zwar wirklich, für mich ist das ein leichter Schock. Für andere würden sagen, nein, das stimmt doch gar nicht. Für mich ist das immer so, ich gehe jetzt heim wieder, wie passiert so etwas und wie kann das sein, wenn ich Studien habe?
Really? Yeah. And?
So I want to wrap up there and summarise by highlighting a few challenges around AI for journalism. Jonathan Stray identifies 5 in particular. The first is the availability of data. In order to use AI or use machine learning specifically, you need a training data set. So you need a reasonable amount of data to train your algorithm on. So in the case of the Instagram and the fake followers, that might be available, there might be a data set around that, but if not, you're going to have to invest time and energy creating that training data set. Related to that, the second challenge is amortization. In other words, is it going to be worth the money? Amortization is the idea that the money that you spend on something has a value over a period of time. And the big problem for data journalism, or journalism specifically, is that most of the things we do are very time sensitive and they're only newsworthy for a certain amount of time. That's very different to something like a Netflix recommendation system, which is going to be used over and over for years and years. And that's another reason why AI is used a lot more often on the back end of journalism for things like story recommendation or ad pricing rather than one-off stories. So we need to look for opportunities to use this where, for example, the story might be ongoing or happen over and over again. The third challenge is obviously the difficulty. This is not an easy thing to do. And the fourth challenge is accuracy. We've touched on some of the issues around these are never going to be perfect algorithms. And it's useful to look at examples like SRF where they acknowledge the 94% accuracy of the algorithm. And you will have noticed, hopefully, that they said about a third of followers are fake. We can't be precise. Now, where that accuracy is important, we might not be able to tell a story. We might not have a story. So that lack of accuracy means we can only tell stories within a certain ballpark, or we can estimate certain figures or ranges, or where we've got enough accuracy to be able to go to someone and present some evidence, and a response becomes the story instead. And again, we've got the cost effectiveness of this approach versus using a manual method. Sometimes it's just going to be cheaper to do this manually rather than doing it in a very fancy technical way. For example, the ProPublica story on the spy planes, Peter Aldous says that actually they probably could have done that story without using machine learning and done it more easily. This is just one example to finish off with in terms of that idea of accuracy. This is a story about dialogue in Game of Thrones. This used machine learning to classify speech as to whether it was female or male. So it was fed all the seasons, and you can see these percentage values. But also you might notice at the bottom of the graphic in a minute, the margin of error of plus or minus 8 percentage points. Quite a large margin of error, which means that probably all of these figures are not statistically meaningful enough differences from each other. So season 8 is 22% female, season 7 was 31%. Well, because of that margin of error, season 8 could quite easily be as high as 30%, and season 7 could be as low as 23%. So there's actually no significant difference between those seasons. Of course, overall, there is a meaningful difference between male and female, and that is the story. So that's okay. That means we can report that story, but we couldn't say that there was a difference between one season and another. So just to sum up the key points from this video, the first is to be aware of the new possibilities that machine learning opens up for journalism, particularly around things like finding needles in haystacks, or being able to classify large amounts of documents or images or things like followers on Instagram, but also to be aware of the risks that that introduces into our processes. Secondly, be aware of the different tools and what they can do, the difference between supervised learning and its ability to classify, for example, and unsupervised learning and its ability to identify clusters. Be aware of natural language processing and the different possibilities within that. And finally, transparency is important in this field, not just in terms of our audience being able to understand how we arrived at the findings that we did, but also internally it's important in allowing others to audit what we've done, to be able to test the algorithm, and to be able to review it if we're going to use it on an ongoing basis. There's a lot of reading around this subject, and on Moodle you'll find a link to the article How to Think About Bots, which is related to automation. Likewise, Jones and Jones's piece of research on structured journalism is well worth reading as well. And really anything by Nicholas Diakopoulos when it comes to algorithms and accountability is well worth looking at. I'd thoroughly recommend you read at least one piece of research by Diakopoulos, and indeed his book, which is on automation in the news industry.